that, of course, is all but over. We have the LHC now being prepared for the next run with much improved, many improvements on the accelerators, but also on the experiments. We have the high luminosity LHC around the corner, and since the summer, we have the approval from CERN Council for a study for the future circular collider. And we are glad that Fabiola Gianotti, the CERN DG, has agreed to give us perhaps a glimpse into the future, the next 50 years of hadron colliders. Fabiola, please.
Thank you. So I would like to tell you welcome at 6 o'clock, and as last speaker I think is a little bit ridiculous. So let me just tell you that I'm very, very pleased to see many of you back at CERN and to walk through a big chunk of CERN history, and I'm also very, very pleased to have the opportunity to talk about the future. So the short, medium-term future, the high luminosity LHC, and the longer-term future, so a possible future higher energy collider at CERN. So I will start with iLumi, and maybe a short reminder for those of you who have not been connected to CERN in the past months. After very successful Run 1 and Run 2, we are now completing Long Shutdown 2, during which we upgraded significantly the injectors. And actually, now they are back into operation, and just after a few months into commissioning and operation, they've been able, in some cases, to reach the performance expected for high luminosity LHC. One example is given here. For instance, you see the brightness of the booster beam in terms of emittance versus intensity, which have already achieved the target performance for high luminosity. In parallel, the LHC experiments have completed their phase 1 upgrades. They are completing their phase 1 upgrades, which were particularly significant for LHCb and ALICE. We plan to start Run 3 in February 2022 at a center of mass energy of 13.6 TeV, so another jump up. According to the current schedule, Run 3 will end at the end of 2024, but this schedule at the moment is being reassessed. What's going on here? So by the end of 2024, we will finish Run 3, and this is the end of the nominal LHC, and the goal is to deliver to Atlas and CMS an integrated luminosity of at least 350 inverse femtobar. Then, during LS3, the upgraded components of the collider will be installed, as well as the phase 2 upgrades of Atlas and CMS. And then high luminosity LHC will start with the target peak luminosity between 5 and 7.5 times 10 to the 34 level, so a factor of 5 to 7.5 larger than the design luminosity, nominal luminosity of the LHC, with the goal of delivering over a time scale of 10 years a total integrated luminosity which is a factor of 10 larger than at the end of the nominal LHC. So the high luminosity upgrade of the collider consists in replacing some 1.2 kilometers of accelerator with new technology. And here you can see the main components, which range from new superconducting magnets providing higher field, 11-12 Tesla compared to 8 Tesla for the LHC magnets, to new collimators for machine protection given the higher intensity of the beams, to new superconducting link for cold powering, to crab cavities for tilting the bunches and therefore providing higher luminosity. Now, as you can see here from these red sketches, the installation of these components and their services required massive civil engineering underground work around the Atlas and CMS interaction points, building new galleries and caverns to host the components of the upgrade. And this underground civil engineering work, more than 1 kilometer, has been completed in a long shutdown 2 as planned. The sketch below shows the complexity of the long straight section at both ends of the two colliding points at Atlas and CMS. Here you can see the LHC tunnel, and then here you can see the new excavated galleries and caverns, which will host, for instance, machine protection and power converters, etc. Now, one of the most challenging components of the high luminosity upgrade of the LHC is the development of new higher field magnets, 11-12 Tesla, based on the niobium-13 technology. And these are dipoles originally foreseen to give more place for collimators, and the final focus quadrupole, so the so-called inner triplet. And this slide summarizes the current status of in terms of training of these magnets to the final current. So at CERN, we have produced 4 full-length dipoles. They've all been tested. They've all reached nominal current, which is 12 kiloamps, but you see that after thermal cycles, they show performance degradation. Fermilab has built 4 full-length quadruples. Full-length means 4.2 meters for the quadruples built in the US. They've been tested up to nominal current. They all reach the nominal current, and the performance is stable. At CERN, we have tested 2 full-length quadruples, 7.2 meters long. They are longer than one at Fermilab, and they do not show a fully satisfactory performance. So the conclusion from this is that there has been huge progress on the niobium-13 technology, as demonstrated by the successful US program, by the fact that most of the CERN magnets actually do reach nominal current quite quickly, but there is still some work to do at the level of manufacturing processes, and also in particular magnet assembly, in particular preloads, pressure and stresses. But we will get there. The challenges are formidable also for the experiments, because the higher peak luminosity produces a much harsher environment at the LHC than the high luminosity LHC than at the nominal LHC. So, for instance, you see, the number of simultaneous interaction per bunch crossing, the so-called pile-up, which at LHC is a broad distribution, but in average something like 30 events per crossing. Chris was mentioning 1 event per crossing, but this was many, many years ago. So during run 2, we reached 30 events per crossing, and you can see that at a high luminosity LHC, the number of events per crossing will be between 140 and 200 events overlapping at the same time. And this, of course, requires significant upgrades of the detectors in terms of increased radiation hardness, granularity, more clever triggers, faster and more granular readout electronics, larger bandwidths, etc., in order to provide similar detector performance or better detector performance in the high luminosity environment as today at the LHC, so as to exploit the full physics potential provided by the 10 times more data. Now, this figure looks like mission impossible. However, I would like to recall that when we designed the LHC experiments back in the early 90s, we were expecting a pile-up of something like 20 events per crossing. But actually, the experiment has been able to cope, thanks to the extraordinary performance of the detector and the sophisticated analysis and reconstruction technique. You can see here a very nice event from CMS with almost 80 overlapping minimum bias event and the precise reconstruction of the vertices. So there has been a great improvement. And for the high luminosity LHC phase, the experiments will also have a new timing detector with resolution around 30 picoseconds, which will provide a 4th dimension for the reconstruction of the primary vertex, and then helping in the disentangle of the various vertices and determination of the primary. So this slide summarizes the most challenging upgrade components in the 2 experiments. So in Atlas, this is for sure the new Atlas tracker is a full silicon tracker like in CMS with extended rapidity coverage, many layers of pixel and strips and rings of strips and pixel for redundancy and for robust reconstruction, very high granularity for a total of 5 billion channels, 50 times more than the current detector. And you can appreciate the increase in size and complexity by comparing the current Atlas pixel detector, highlighted here in yellow, with the new pixel detector for high luminosity LHC. In CMS, the most ambitious upgrade project is for sure the high granularity NCAP electromagnetic calorimeter, which building on the Calice development for the ILC, provides unprecedented lateral and longitudinal segmentation for efficient particle flow reconstruction and pile-up rejection. It's a sampling calorimeter with silicon pads as active layers in the region most exposed to radiation for a total area of silicon of 600 square meters. So we'll now show a couple of examples of the physics potential coming from the increased sensitivity and the better detector performance, and due in particular to the larger amount of data. Starting with the Higgs measurement, the Higgs coupling, as you can see from this figure, can be measured, Higgs couplings to gauge bosons and to fermions of the third generation and to mu, can be measured with a precision much better than 5% in most cases, which represents a factor of 2 to 3 improvement on the precision that the experiment will reach at the end of the LHC. Perhaps most importantly, in the high luminosity LHC phase, ATLAS and CMS together will provide the first observation at the 4 sigma level of the production of pairs of Higgs boson, and this process gives access to the Higgs potential in the standard model Lagrangian, which in turn gives insight into the electroweak symmetry breaking mechanism, in the nature of the electroweak phase transition in the early universe, and I will come back to this later on, and in the vacuum stability. And you can see that this trilinear coupling lambda can be constrained with the interesting, over the interesting range 0.5 to 1.5 of the standard model expectation by combining the most sensitive channels. Of course, more data means higher, larger discovery potential. Typically, the discovery potential, direct discovery potential, increases by 20 to 30% at high lumi compared to the LHC in terms of masses of the new particles. ALICE and LHCb also plan a second major upgrade during long shutdown 4. And LHCb in particular plans to run at high luminosity, more than 10 to the 34, and so to integrate something like 300 inverse femtobarn. And previous speaker has already mentioned the recent anomalies observed in LHCb related to lepton flavor universality possible violation. In particular, this ratio RK, which shows the ratio between the branching ratio of B plus going to kaon and muon pairs and B plus going to kaon and electrons, which is 3.1 sigma below 1. And you can see in this figure that LHCb with 300 inverse femtobarn will be able not only to in some sense constrain the underlying theory, but also to disentangle between possible different couplings and different operators. I'm now going to move to the future and just recall that the European Strategy for Particle Physics, which was updated in June last year, has recommended a study to investigate the technical and financial feasibility of a future hadron collider at CERN with a center of mass energy of at least 100 TeV and with an electron-positron Higgs and electroweak factory as a possible first stage. So what is the time scale of such a project? Well, we just started a feasibility study, which we plan to complete by the end of 2025. Then if the project goes ahead and if it is approved before the end of the decade, then construction of the tunnel and the first stage machine, FCC-EE, could start at the beginning of 2030s. FCC-EE operation could realistically, say, assuming the funding is there, run for 15 years between 2045 and 2060, and this will be followed by 25 years operation of a FCC-HH, the Hadron Collider, starting in 2070 or so. So a 70-year-long program, and a very rich one, as you can see from this table, in terms of different colliding particles, E plus, E minus, proton-proton, different heavy ion species, electron-proton, etc., different energy ranges and explored, and all of them with unprecedented luminosities. So this table compares the main parameters of the proton-proton collider, FCC-HH, with high lumi and LHC. So I'm not going to go through all of them, I just draw your attention to a few of them. We are targeting a center of mass energy of at least 100 TeV in a 90-kilometer tunnel. I will come back to this 90 later on, with a peak luminosity which will reach 3 times 10 to the 35 and which will allow over a 25-year operation to integrate something like 20 to 30 inverse Abtuban per experiment. So this is very nice, but the challenges are clearly daunting. First of all, we need high-field superconducting magnets reaching at least 16 Tesla. Synchrotron radiation is an issue, even a proton collider at this energy, so the power load in the arcs will reach 5 megawatts, so this of course has consequences and challenges for cryogenics, vacuum and beam screen. The store beam energy, 8 gigajoule, will be a factor of 20 larger than currently at the LHC, so machine protection issues. The detector will suffer from a pileup of 1,000 events per crossing, so yet another step. And the current estimate of the energy consumption is 4 terawatt-hour per year, which is a factor of 3 larger than what we are consuming today. And of course, this must be reduced, and so requires R&D on cryogenics, pushing high-temperature superconductor, etc. And of course, people are working on this. I don't think I have the time to discuss the high-field magnets program, which is a pillar for a future hadron collider like FCC-HH. Let me just mention that we are working in 2 different directions, so along the 2 axes of this plot. On one end, pushing niobium-13 up to the ultimate field, as close as possible to 16 TeV, and developing high-temperature superconductor to go beyond 20 Tesla or so. And then on the other axis, using lower field magnets like those that we are building for high luminosity LHC, work on the development of a robust construction processes, manufacturing, and cost-effective procedures, so as to be able to build 4,500 magnets needed for a 90-kilometer tunnel at an affordable cost. And last year, we have doubled the CERN budget invested on this important R&D. So to introduce the physics potential, let me emphasize that FCC-HH will be an unprecedented factory of essentially all known particles and also many of the unknown particles which are hopefully there. This table shows the ratio of cross-section 100 TeV over 14 TeV, and of course, as expected, the highest gain is for the most massive process, so a factor of 30 increase in cross-section for TT bar, 60 for TT bar Higgs, 40 for Higgs boson pair production. And this large cross-section combined with a huge integrated luminosity will provide extraordinary data sample. For instance, 100 billion of TOPS, 1 billion of TT bar Higgs, 10 million of Higgs pair, etc. And with these statistics, of course, we are going to do the 2 traditional things. First of all, explore in a direct way the new energy frontier. LHC has been able to explore the 1 TeV scale up to, say, 10 TeV or so. This machine will make a jump a factor of 5 or so to 7. So you see from this figure, from this table, that such a machine should be able to discover new particles up to 50 TeV or so in a huge number of scenarios, which are chosen here just for illustration, from composite to new gauge bosons to gravitons, etc. The other thing that the FCC-HH will be to achieve ultimate precision on some Higgs couplings, and where FCC-HH can do better than the previous machine, and this is indicated here by the arrows, is for 2 classes of Higgs couplings. Those that are extracted from rare final states, like X2 mu mu, X2 gamma gamma, X2 z gamma, and those that are extracted from heavy final states, like TT bar Higgs and the self-couplings, which come from the dye boson production. So this plot shows what I consider the ultimate precision in the measurement of the Higgs coupling by combining high Lumi and the full FCC program. The ultimate results are these light green bars, and you can see that most of them are measured at the level of a few per mil, which give access to quantum correction in the Higgs sector. But I would like to say that perhaps more importantly, in my opinion, FCC-HH will provide definitive answer to several structural questions. First of all, conclusive elucidation of the electroweak symmetry breaking, because FCC-HH will be able to prove the standard model in the regime where electroweak symmetry is restored, so much larger than the electroweak scale of 246 GeV or so. And so it's a crucial test, also a crucial closure test, to demonstrate in particular that the Higgs boson does its jobs, which is regularizing the divergences of the theory. Or else, if this doesn't happen, then discover new physics. So we should say the final words about electroweak symmetry grating. Another definitive answer will come on a class of dark matter candidates called WIMPs, weakly interactive massive particles, which were in thermal equilibrium in the early universe. This is a pretty motivated class of dark matter particles which have some upper bound in terms of mass limit at the level of 1 to 3 TeV, and such a machine can clearly explore the full parameter space. And then the third one is elucidating the nature of the electroweak phase transition in the early universe. So was this transition smooth as in the standard model, or was it a first order strong transition as it is required by baryogenesis? So in which case the Higgs potential in the standard model that I showed before will be modified. And now the very precise measurement of the Higgs coupling, including the self coupling at FCC, combined with the discovery potential for new massive Higgs boson, will allow the FCC to say, most likely, a final word about the nature of this transition. I don't have the time to discuss the detectors. I will just say that the concept for general purpose detector at FCC HH have been developed in order to optimize the physics reach and at the same time to face the challenges, pile up, etc. And before concluding, I would like to say a few words on the ongoing FCC feasibility study, whose high-level objectives are summarized in this slide. So, first of all, demonstration of the geological, technical, environmental, and administrative feasibility of the tunnel and the surface areas. Second, optimization of the design of the colliders and their injector chains, supported, of course, by the needed R&D on the key technologies. The elaboration of a sustainable operational model for the colliders and the experiments in terms of human and financial resources, as well as environmental aspects and energy efficiency. We need to develop also a consolidated cost estimate and funding model, and in parallel, identify substantial resources, we are talking about billions, from outside the CERN budget. And of course, last but not least, consolidate the physics case and the detector concept. And the results of this work will be summarized in a feasibility study report, which will be released by the end of 2025. Before concluding, would like just to flash one recent important step of the feasibility study, very good progress. We have recently converged on a baseline scenario for the placement of the ring with two fallback solutions, down from originally more than 50 variants. And this will be a ring with a circumference of 90 kilometers, and we went down from 12 surface sites to 8 surface sites, which I think is very good, and this is the corresponding machine layout. This figure here illustrates the territorial and the complexity of the territorial and environmental constraints that we had to take into account in order to find a suitable place for the ring. So I'm now coming to my conclusion. The full exploitation of the LHC, including the high luminosity phase and future high energy and high luminosity colliders, are absolutely necessary, in my opinion, to improve our knowledge of fundamental physics. Historically, hadron colliders, as we have heard, have been one of our most powerful tools for exploration in particle physics, and I believe they will continue to play a crucial role also in the future. And let me say also that the extraordinary success of the LHC, with the accelerator, experiments, and computing performing well beyond the design expectation and a much richer physics program than initially planned, is clearly the result of the vision, creativity, and perseverance of our worldwide community, and more than 30 years of hard work, and many of the people who have made the LHC possible are in this room. And I believe that this success demonstrate the strength of our community. And for me, it's a necessary milestone in order to be credible when proposing future and even more ambitious projects. Thank you very much.
Thank you very much, Fabiola, for the excellent summary. We are running a bit over time, but if there is an urgent question, I'm sure that Fabiola would be happy to answer.
No urgent question. Dinner.
You have been too clear.
Dinner time. Oh, it's rather fatigue and dinner time.
Thanks a lot again.
Thank you.
That brings us to the end. Freddy, we should thank all the speakers.
I think we have to thank all the speakers for the very nice. And all the best for the next 50 years.
Exactly. We're looking forward to it. Thank you. Okay.